So to my Phys 205 students who are taking the exam this week, when you get the exam, take a deep breath, collect your thoughts, and read through every single one of the exam questions. I always recommend that you start the easiest ones, just to give yourself a little boost in confidence, but there will likely be problems that you struggle with. When you get to those problems, at the very least, write out what it is that you know. So whether that be relevant equations or a diagram, literally anything is better than nothing. Of course, this doesn't apply to multiple choice questions, but for the long form questions, if I see that you've made an attempt, I can award partial marks for that. Of course, I won't be grading all of the exams, but most TAs do think the same way like that. So of course, while I hope that all of you do really well, pass with flying colors, I know that that is unlikely to happen. And if you don't do as well as you hoped you would, or if you failed the class, just remember that that is okay. Like, it's not some giant stain on your academic career or judgment on you as a person. Some of the smartest people I know have failed classes. Like, I got some of the worst grades I've ever gotten in my life during my first year at university. Like, these classes are very far from easy. But anyways, so in this video, I'll be going over a lot of the equations that we have seen during this class, but I'm not going to be explaining what exactly each of them mean. Like, I feel like I've done an okay job doing that in my theory videos. So here, for instance, I'm going to be giving you the general topic and the chapter. So say, for instance, there's an equation in here that you don't think you've ever seen before, or you have no idea what it's talking about. Go back to the chapter, look up the theory, figure out what the equation means, and try to do some problems that are related to that equation. One more thing, so on my YouTube page, there's a link to the Google Drive that contains all of my notes, and there's some mistakes in them, so I have like this Google Doc where you can write a comment and say like, there's a problem, and then one day I will probably fix it. So most equation sheets do have a physical constant section. I'm not going to be spending too much time here because you don't really need to have an in-depth knowledge as to like what every single one of these constants physically means. You just have to know that you have access to them and that they all have units, right? Like, if you start forgetting your units in your equation, you are much more likely to get an answer that has the wrong units, which is not the right answer. But anyways, you can pause, have a look here, or just go to the Google Drive and download the PDF. But anyways, I'm going to start off with chapter 32, which was AC circuit. So I'm going to be going backwards from 32 all the way down to 22. Here, we talked about XL and XC. This is the inductive reactance and the capacitive reactance. The idea is that in AC circuits, the current is going one way, and then it flips, and it goes the other way. And it flips with an angular frequency of omega. So our inductor and our capacitor kind of react to that flipping of current directions in a way that's really similar to resistance. So this is like the resistance of the inductor in an AC circuit. So we have omega and L, where L is the inductance. So this is XC. The combination of the resistance from the resistor, from the inductor and the capacitor is called the impedance, and it's Z. And then we also have phi, which is the phase angle between the max voltage and the current. So hopefully you remember this little diagram where we had, say, like I max, and then we had delta V max, and then we have this offset, which is phi. It's just saying that the maximum potential is not reached at the same moment as the maximum current, which it normally is when we just have like a DC circuit. We have all of these equations here, where this is really just like the current going through a resistor, inductor, and capacitor, where this part, this is I max, like the maximum current. This is pretty normal, like delta V max divided by R, where here for the inductor we don't have R, but instead we have XL. And then here we have XC. And then we have this phase difference here as well. We have Q, which is the charge on the capacitor. Pretty similar. This is Q max, and then we have sine omega t because, again, AC circuit. These three equations, super similar to these three. It's just saying what is the potential across the resistor, capacitor, and the inductor. And this is the equation for delta V max. It's just going to be I max times Z. You're used to seeing I max times R, but in AC we call it Z because it's impedance, not resistance. Anyways, most of the problems in chapter 32 were literally just figuring out all of these components that you had a certain setup, like a scenario, and then you have to figure out what is XL, what is XC, what is phi. So if you're struggling with that, do some of those questions. So here, these are some of the equations from chapters 30 and 31, where we have Faraday's law here, which is saying that a change in magnetic flux is going to induce an EMF. And we also saw a whole bunch about Lenz's law here. That's just the negative sign. We also saw the motional EMF whenever we had this scenario. So we had a circuit and we had this component here that I'm just going to color in green, and say this component of the circuit was moving with a velocity v going to the right. This movement of this component here led to us having a current going through this circuit around here. And this was just the equation that we found. And this, of course, was for when we had this nice uniform magnetic field that everything was moving inside of. We also talked in chapter 31 about self-inductance, and that had to do with the fact that whenever we open or close a switch in a circuit, we get this EMF that's going in the backwards direction. So just if I remind you, let's say we have an inductor, resistor, doesn't really matter, and we have a switch. So it's open, there's no current, we close it, all of a sudden there is current. So there's this change in current, which means that there's a change in the magnetic flux. Because there's a change in the magnetic flux, we have an induced EMF. And that's represented here, where L is the inductance, which is found just by comparing these two equations to be N phi B over I. We saw that solenoids are really good inductors, so usually we're talking about solenoids in our circuit here. And we then found that we could talk about the current in this circuit using these two equations here, where essentially the current doesn't go from 0 to 100%, but actually takes some time. And we saw when we drew the graphs that it starts off at 0, we close the switch, it takes some time, and then it reaches its maximum value. And that is this equation here, where tau is our time constant, which is just L divided by R. We also saw that whenever we open the switch, we don't go from 100% to 0, but the current actually, again, takes some time to decrease, right? And then eventually, it does reach 0. And that's just right here. We also saw UB is equal to 1/2 Li squared, which is the energy stored in the magnetic field of the inductor. Whenever we were talking about LC circuits then, we saw that the total energy of the system is either in the L, the inductor, or C, the capacitor. So this is the capacitor, and this is the inductor. And if there's no resistor or any loss, that energy is going to stay there forever and just kind of flip-flop between, is the energy stored in the electric field or is the energy stored in the magnetic field? For this circuit, so an LC circuit, we talked about Q of T, just saying, okay, where is the charge? Is the charge on the top plate of the capacitor? Is it positive here and negative here? How much charge is built up? Or is it negative and then positive? Because we saw that it would flip. And it would flip with this rate. Omega is equal to 1 over square root of LC. We also looked at the current. Where was the current flowing? Is it flowing in this direction or is it flowing in this direction? How much current do we have? Because we saw that would fluctuate too between because we had an L and a C component. So in chapter 28, we kind of just assumed that there was a magnetic field, and we saw that particles experience a magnetic force if they were moving inside of that field. So here, this is the equation that we saw, where we have Q, V cross B. Normally, you are expected to solve cross products, so remind yourself how to do that. We also saw how to add up electric forces and magnetic forces. This is called the Lorentz force. One more thing that we saw here is that, let's say we have a uniform magnetic field and we have a charge moving into it. So it has a certain velocity and it's going in. We saw that it's actually going to start going in a circle. The direction that it goes in, is if it's going clockwise or counterclockwise, depends on its sign, is it positive or negative, and where is the magnetic field pointing. But we saw that we could calculate the radius of curvature, how big that circle is, using this equation here. We also saw the magnetic force on a wire, which is this equation here. If it's just a very simple straight wire, we can use this equation. If it is, say, like a curved wire or something, we have to divide it up into little components and calculate the force on every component of that wire. We saw the torque on a loop of area A, so this is just our generic equation for torque, and we saw that here there should be a area or a vector sign here. It's like I, the current going through the loop, the area vector across the magnetic field. So that was chapter 28. And then in chapter 29, we looked at Biot-Savart's law. So we saw like, okay, where does that magnetic field actually come from? And we saw that it can be due to a current carrying wire. So really any moving current makes this magnetic field. If it's in a wire, well, it's a lot easier to deal with because it's all in the same region. So we have Biot-Savart's law. Whenever we have an infinite wire, it becomes a lot more simple, and we get this equation. Whenever it is a solenoid, it's even more simple, because with a solenoid, the magnetic field is really nice and uniform going through it like this. So my current's going like this, my magnetic field is going in that same direction here. We also looked at Gauss's law in magnetism, and we essentially saw that no magnetic monopoles exist. So here, like the closed surface integral of B dot dA has to be equal to 0. In chapter 27, we started off by looking at the difference between the EMF, electromotive force, and delta V, the potential difference across the battery. And we saw that normally the EMF is larger than delta V battery because this is ideal. This includes some internal resistance. We've been a little bit loose because you're kind of just going to be given something, you're going to be told, okay, the potential at the battery is 10 volts. And you're going to assume that that's already taking into account any internal resistance, so you don't really have to think about it much, but there is a distinction. We saw how to add up resistors whenever they're in series and whenever they are in parallel. We also looked at RC circuits where we had a resistor and a capacitor, and we saw that the charge, like the capacitors don't fully charge straight away, they take some time. How much time it takes? Well, it's by this equation here, where C times E is the maximum charge the capacitor can hold. And we see here that we have RC. This is our time constant in this case. This is for the charging case, and then this is for the discharging case, where we have a full capacitor, and then we let it discharge through a resistor. It doesn't just discharge immediately, it takes a certain amount of time. In this chapter, we also looked at the Kirchhoff loop and junction rules. So those are really important whenever we have like multiple battery systems or things that get a little bit more complicated and you need to figure out what is the current at every point around here. In chapter 26, we learned about current, resistance, and power, where this is the definition of current. I is equal to dq over dt. We looked at current density, which is just current per unit area. We learned that this is Ohm's law, where J is equal to, so the current density is equal to, this is the conductivity times E, where this is like our electric field. And the idea here is that if a material obeys this Ohm's law, then we can also say that R is equal to delta V divided by I. And we kind of called the second one Ohm's law. Well, I mean, like this one is, but it doesn't really matter. Something else that's important is rho. Rho is a resistivity. So it's like how resistive is this material to having things move through it. And it is the inverse of the conductivity, which is like how conductive is the material. The most important equation here is really this one. R is equal to delta V divided by I, as well as these power equations here, where it's like how much power is being consumed by the resistor or the battery or whatever. You just plug in these equations and you get out some number. In chapter 25, we looked at capacitors and dielectric materials. This is the definition of capacitance. The one that you really use is C is equal to Q divided by delta V. You learned that there's energy stored in the capacitor in its electric field, and we call that UC or UE, whatever, is equal to Q squared divided by 2C. You learned how to add up capacitors when they're in parallel and in series, and you learned how capacitance changes when it's in the presence of a dielectric material. So whenever we had our capacitor plates and then we inserted a dielectric material here, like it's going to change what the capacitance is according to this equation here, where K is just our dielectric constant. So in chapter 24, we started off by seeing the link between work and electric potential energy, and we saw this equation here where delta UE, so change in electric potential energy, is equal to this, where we're essentially taking a charge from point A to point B. If we have a uniform electric field, so whenever we had these like parallel plates and we had just a charge moving in the same direction as the electric field and everything was very nice, we could have negative QE delta R, where delta R was just like how far did it travel here. This is the electric potential energy of a 2-point charge system. And then we also saw the link between electric potential energy and electric potential, where electric potential is literally just electric potential energy divided by Q, which is going to be this equation here. A relatively important result from this is this link between E and V. So it's like the link between the electric field and the potential, where this is a scalar field and this is a vector field, is this equation here, and we did a couple problems related to that. I should note that around this point is where kinematic equations started to become a little bit more useful. Like they're kind of spread out within the material, but hopefully you would be provided those. Say for instance you have, I don't know, like an initial velocity, initial position, and you need to figure out like what's the final velocity. Like kinematic equations obviously come in handy there. So going all the way back to chapter 22 now, we saw Coulomb's law, which is just saying the electric force between two charged particles. We also looked at E, which is the electric field, which is just Fe, electric force, divided by the charge, and we got that equation here. We also saw that if we have many point charges, we can add up all their contributions to the electric field, or if we have a continuous distribution of charge, we sum them up like so. This equation here just comes from the motion of a charged particle in a uniform electric field, where we have, say, the sum of all the forces is just equal to Q times E is equal to mass times acceleration, isolate for acceleration, and you get that here. This is the electric flux, where we have the integral of E dot dA, and then we have Gauss's law, where we have the flux over a closed surface is equal to Qn over epsilon naught. That came in handy a couple of times. This equation here, I didn't really know where to put it, but it's essentially the electric field due to an infinite plane of charge. And it comes in handy whenever we're dealing with problems where we have like this parallel plate system and we want to know like what is the electric field here. Well, we just have to remember that we have two infinite planes of charge and multiply that by 2. I recommend that you know your basic integrals. Maybe you'll be given integrals. I don't really know, but the basic ones should be enough. Also, this is just an equation that popped up once in a while, arc length, so S is equal to R times theta.